Every day, a chart recorder in a field outside Cambridge printed about 30 meters of paper. A pen twitched up and down as the sky moved overhead and left a wavering line behind it. Somebody had to read all of it. By eye. That somebody was a 24-year-old postgraduate student, and over the course of her PhD, she went through something like 5 kilometers of it. On one of those pages, she noticed about a quarter of an inch of something that did not belong. She called it a bit of scruff, about 6 millimeters of ink, on a roll of paper in a filing cabinet among several kilometers of nearly identical ink. It turned out to be an object nobody had ever seen, a collapsed star, the mass of our sun packed into something the size of a city, spinning fast enough to sweep a beam past the Earth once every 1 1/3 seconds, and to have kept doing it without missing ever since. 7 years later, the Nobel Prize was awarded for that discovery. Her name was not on it. This is the whole story, including the part where she refuses to be bitter about it, which is somehow the most interesting part of all. Susan Jocelyn Bell was born in Lurgan, County Armagh, in 1943. Her father was an architect. Among the buildings he worked on was the Armagh Planetarium, and she read the astronomy books he brought home from it. The staff there encouraged her, though she has said they assumed she wanted to be a secretary. At her first school, when the class was old enough to specialize, the boys were sent to the science laboratory, and the girls were sent to learn cookery and needlework. Her parents objected. So did some others. She and 2 other girls were moved into the science class. She came top of it. It is worth pausing on how close that came to not happening. The default was the needlework room, and the only reason she was in the laboratory was that somebody complained. She was sent to a Quaker boarding school in York, then read physics at Glasgow, graduating in 1965. She was the only woman in her honors physics class. The custom, when a woman entered the lecture theater, was for the men to whistle and bang the desks. She sat through it for 4 years. She has said she did not take it personally and simply got on with it. Then Cambridge, and a supervisor called Anthony Hewish, and a project that began with 2 years of manual labor. Hewish wanted to study quasars, extremely distant, extremely bright objects that had only just been identified. Quasars had only recently been identified. Nobody knew what they were, only that something very small was producing an extraordinary amount of energy. His method depended on something called interplanetary scintillation. Radio waves from a very small, very distant source twinkle as they pass through the solar wind, in the same way starlight twinkles through our atmosphere. To catch that twinkling, you need a radio telescope with an enormous collecting area and a very fast response. So, they built one in a field, 4 acres of it. 4,096 dipole aerials strung on more than 1,000 posts, wired together by hand. 2,000 miles of wire and cable, in a field, assembled by a team of 5. Bell was there with a sledgehammer driving in posts for 2 years. This is not a detail people expect in the story of a Nobel-winning discovery. Before the physics, there was fencing wire, wooden mallets, and a field in Cambridgeshire in the rain. She has said she was the only person on the project who knew where every cable went, because she had laid most of them. It was tuned to 81.5 megahertz, a wavelength of about 3.7 meters. In July 1967, it switched on, and the paper started coming. There was no computer to look at it. There was her. The array had no way of pointing. It stared straight up, and the rotation of the Earth dragged the sky across it. The array covered the whole visible sky every 4 days, and every 4 days produced another 30 meters of trace to be read. She learned to recognize the shape of a quasar scintillating. She learned to recognize interference from cars, from thermostats, from a badly suppressed motorbike. This is the part of the discovery that gets skipped. Before she could recognize something impossible, she had to know, from the shape of a pen stroke, everything that was ordinary. The signal was there in the data taken in August. Nobody saw it at the time. She did not spot it in August. The papers had to be checked by hand, and she was months behind. It took her until the 28th of November to work back to it. What made her go back was that the scruff kept turning up in the same patch of sky. Not at the same time each night, 4 minutes earlier each night. That 4 minutes matters enormously. Local interference keeps clock time. The stars keep sidereal time and run 4 minutes fast. Whatever this was, it was not in the building, and it was not on Earth. Hewish's first assumption was that it was interference, and his second was that it was a fault. Neither is unreasonable. Both were wrong. She kept going back to it anyway. So she asked for the recorder to be run fast, to stretch the signal out and see its shape. For weeks, the source refused to appear while the fast recorder was running. When it finally did, On the 28th of November, the scruff resolved into something nobody expected. A pulse. Then another, spaced 1 1/3 seconds apart. There was nothing in astronomy that behaved like this. The fastest known variable stars took hours, 1.337 seconds to be exact, and holding that interval to a precision that made no sense. Here's why that was a problem in 1967. Astronomical objects were not supposed to keep time like that. Things in space are enormous, and enormous things are slow and sloppy. A star cannot rotate once a second. It would tear itself apart long before it got there. Something the size of a planet cannot pulse once a second either. So the first serious hypothesis was that it was people. A satellite, a radar station, a fault in their own equipment. They ruled out the obvious sources one by one. The period was too stable for a satellite. It reappeared on the correct sidereal schedule. They checked. They had another observatory look for it, and it was there too, so it was not their wiring, which left the possibility that was, briefly, taken seriously enough to write down. A signal that regular, from a source that small, might be a beacon. Deliberately produced. By somebody. They labeled the source LGM-1. Little Green Man 1. The name was a joke that also functioned as a placeholder, which is exactly what a good placeholder does. It holds the space without pretending to be an answer. Bell has been clear that they never really believed it, but they could not rule it out, and the implications were sitting there. There was a real discussion about what to do if it were real, whether it was theirs to announce, and who would have to be told. Her own account is closer to irritation than wonder. Here was she, trying to get a PhD out of a new technique, and some silly lot of little green men had chosen her frequency and her aerial to communicate with us. Then, just before Christmas, she found a second one. Different part of the sky, different period. Same impossible regularity. And that settled it. Two independent civilizations on opposite sides of the sky, both signaling this particular field in Cambridgeshire on this particular frequency, was not credible. It was nature. Whatever it was, the universe made more than one. More followed in other parts of the sky, each with its own period. One new kind of object, not one strange event. The paper appeared in Nature on the 24th of February, 1968. It had 5 authors. Hewish was first. Bell was second. Author order in physics is not a formality. First position carries the discovery. Second position is real, and it is not first. Within weeks, the explanation arrived from Thomas Gold and, separately, Fred Hoyle. A rotating neutron star. Neutron stars had been proposed in the 1930s as an arithmetic consequence of what happens when a massive star runs out of fuel and its core collapses. The idea was 33 years old and had been sitting in the literature the whole time, with nobody able to test it. The core falls in on itself until the matter cannot be squeezed any further. What is left is a sphere of neutrons about 20 kilometers across, with more mass than the Sun. A teaspoon of it would weigh about as much as a mountain. The surface gravity is something like 100 billion times the Earth's. Dropping a marshmallow onto one would release energy comparable to a nuclear weapon. For decades, they were a calculation rather than an object anyone had observed. And a collapsing core conserves its angular momentum. Shrink a slowly turning star to the width of a city and it spins up the way a skater spins up by pulling their arms in. It also concentrates its magnetic field to something like 1 trillion times the Earth's. Charged particles are flung out along the magnetic poles as 2 beams. If the magnetic poles are not lined up with the rotation axis, and they usually are not, those beams sweep around the sky like a lighthouse. We only see it when the beam crosses us. That is the pulse. Her 1/4 inch of scruff was a dead star the size of a city, turning 3/4 of a billion times since the paper was published and still keeping time. The pulses she recorded in 1967 are still arriving. They have not missed one. Then the press arrived, and there is a detail from that period worth keeping. The astronomers were asked about the physics. She was asked whether she was taller than Princess Margaret, and how many boyfriends she had. The photographers asked her to undo a button for the pictures. She has told this story many times, and never with much heat in it. In 1974, the Nobel Prize in Physics went to Anthony Hewish for the discovery of pulsars, and to Martin Ryle. The citation credited Hewish for his decisive role in the discovery of pulsars. It was the first Nobel awarded for astronomy. Bell was not included. Fred Hoyle publicly objected. Others did too, and the omission has been argued about ever since. Bell's own position has been consistent for 50 years, and it is not the one people expect. She argues that supervisors do get the credit for their students' work, that this is how the system runs, and that she does not want to be the exception that proves it was fine. She has also said, plainly, that being a graduate student and being a woman, together, lowered her standing in the eyes of the people deciding. Both things can be true, that the convention explains it, and that the convention was wrong. And she has pointed out more than once that she has done rather well out of not winning it. People remember the person who was left out. A Nobel laureate gets one prize and a fortnight of attention. She has been given almost every other honor going for 50 years, partly because of the argument. What she found became one of the most useful objects in physics. Pulsars are clocks. Some of them keep time well enough to rival atomic standards, and because they are scattered across the galaxy, they can be used together as an instrument. They have been used to weigh stars, to test general relativity to extraordinary precision, and as a possible navigation system for spacecraft far from Earth. A binary pulsar gave the first evidence that gravitational waves exist, decades before anyone detected one directly. Arrays of them are now being used to look for the waves themselves. And, in 1979, a record sleeve appeared with a stack of white lines on a black background. It was a plot of successive pulses from her pulsar. It is probably the most reproduced piece of astronomical data in history, and most of the people wearing it have no idea what it is. The plot was made by a radio astronomer called Harold Kraft, stacking one pulse above the next so the variation between them was visible. In 2018, she was given the Special Breakthrough Prize in Fundamental Physics, $3 million. She gave all of it away. The entire sum went to fund graduate scholarships in physics for women, for underrepresented ethnic minorities, and for refugee students. Not a building with her name on it. Studentships, administered by the Institute of Physics for people who would otherwise not get through the door she had to force. Not to an institution, and not to a building. To students who would otherwise struggle to get through the door she had to force. In 2021, she received the Copley Medal, the Royal Society's oldest award. She was the second woman to get it in 280 years. A list of previous recipients includes Benjamin Franklin, Charles Darwin, Albert Einstein, and Dorothy Hodgkin. The trace still exists, 6 millimeters of ink on a roll of paper. It is the moment a graduate student who was months behind on her reading decided that something did not look right and went back to check. Thanks for watching.